Good afternoon. So let me just repeat the discussion of the first example on related rates. There was an error made regarding the follow-up question. Anyway, let's just explain it again. This was the problem. A 10-foot ladder. Remember, you attended that live session or watched the video asynchronously. 10-foot ladder sliding down the wall, away from the wall, the bottom, sliding away from the wall at the given rate of 3 feet per second. And then we wanted to find the rate at which the top of the ladder is sliding down the wall. At the moment, when this bottom here is 8 feet away from the wall. How did we go about solving the problem? Well, this should always be the first thing you need to do whenever you are solving a related rate problem. I will not be giving you a step-by-step procedure here, but the general way in which you should approach the problem. First, you need to find a relation between your variables. And based on the diagram there are only two variables, x and y. Y represents the distance up from the ground, and x the distance of the bottom or the foot of the ladder from the wall. And by the Pythagorean theorem, you can easily find the relation between the two variables. X squared plus y squared equals 100, which we have here. And once you know the relation, the next thing you should do is to differentiate with respect to time. Although in the textbook or from other teachers, you will be taught a different approach. But without being systematic, this is what you just need to do. Find the relation, then differentiate with respect to time. And then the given will follow after. So once you have the relation, you can differentiate with respect to time, the relation. Don't forget that all variables present are now dependent on time. So we have to apply the chain rule for each of the variables there. X is changing with respect to time. Y is changing with respect to time. So chain rule gives us 2x being down to subtract 1, then differentiate the base x with respect to time. Do the same for y, bring down 2, subtract 1, and then differentiate the base y with respect to time. You also have to differentiate the other side of the equation. Okay, and the derivative of a constant with respect to any variable is always 0. So we have that equation from the relation found here. Now, once you have differentiated the relation, it will give you an equation containing the rates of change of the variables with respect to time. And one of them has to be solved. And that depends on what is being asked in the problem. In this case, we're looking for the rate at which the top of the ladder is sliding down, and that is represented by y. So you're looking for dy dt, the rate of change of y with respect to time. So going back, from this equation, this is what we need to solve for. And treating this as just a mere algebraic equation, we can easily solve for dy dt by transposing this one to the other side and dividing by 2y, getting this. Now, it's better if you further simplify so as to not make the substitution complicated later on. So we can rewrite that as follows: negative x over y dx dt. Now, to get the rate of change here, dy dt, which is how fast the top is sliding down the wall, you need several things. You need the value of x at the given moment, the value of y at the given moment, and the rate of change here. Now, that's when you can look look back at the problem and see what are given. Let me just go back to that. Now here, we are given dx dt, which is the rate at which x changes, the rate at which the bottom is moving away from the wall. And since x is increasing, then that means positive 3. Of course, if x is moving towards the wall, that would be negative 3, since x is decreasing in that case. So again, since it's moving away from the wall, x is increasing, so the rate of change should be assigned a positive sign. Now, we are also given the instant when the bottom is 8 feet away from the wall, and that would be x. So we are given the following so far. We are given the instant when the bottom is 8 feet from the wall. Of course, the length of the ladder never changes, and the rate of change of x, positive 3. Now, we still need y. Based on the given here, we need y. We already have x. We already have dx dt. So it remains to solve for y based on what is already given. From the Pythagorean theorem, we had this. So we can use it to solve for y if we know x. X is 8 at the given instant. So if x is 8, you can plug in 8, solve for y, and it's not hard to get y equals 6. It's actually a Pythagorean triple. 3, 4, 5, so multiples of that, 6, 8, 10, and so on. Anyway, you can just use your calculator to get y, plug in x equals 8, then solve for y equals 6. So now that we have all what we need, we can solve for dx dt. Again, we have x equals 8, dx dt equals 3, y equals 6, sorry, solve for dy dt. So dy dt is from the previous line, negative x over y dx dt. So just substitute those given and found values. So we have this and simplify. You get negative 4. And of course, you expect a negative result since the top is sliding down so that y is decreasing. So it's sliding down the wall at the rate of 4 feet per second. So the y value is decreasing at that rate. And then we have this follow-up question. How fast is the angle between the ladder and the ground changing at the same instant given in the problem? So this is the graphical representation or the free body diagram where now we are being asked for the rate of change of this angle, which we denote by theta. So we are looking for d theta over dt, the rate of change of theta with respect to time. And to be able to do that or find that, we need a relation again, relating theta with the other variables, maybe all of the variables or maybe just one of the variables. Now we can use trigonometry to derive a relation between x, y, and theta. And we can use sine, we can use cosine, depends. So let me just use cosine. You can use also sine. But if we use cosine, then we know that cosine is, remember, adjacent over hypotenuse. Sine is opposite over hypotenuse. So if we use cosine, it will be x over 10. Then this one gives us a relation between theta and x, which again, after you get, remember I said a while ago that once you have a relation, you differentiate with respect to time. So differentiating that, left-hand side with respect to time, right-hand side with respect to time, then applying the rules for cosine and the other rules, chain rule. The derivative of cosine, remember, is negative sine. And then don't forget to differentiate the quantity inside cosine with respect to the variable t. And also this one, this is just over 10, so we can take it out. It's 1 over 10. Sorry, this should be positive. And you just differentiate x with respect to t. So this gives us, if you divide by negative sine theta, Okay, we have -1/10 sine theta, so this should be positive, but this is correct now. -1/10 sine theta dx dt. So to get what you're looking for, which is the angular rate of change, d theta dt, you need dx dt, already known, and you just need one more, sine theta. You don't need theta, by the way, you just need sine theta, which can be derived from the figure here. A sine is opposite over hypotenuse, so it's y/10. Okay. Again, we already know x, we already know the x dt from before. So it remains to find sine theta. Sine theta is opposite over hypotenuse. So y/10. And y at that instant, at the instant when x is 8, we got y to be 6. So it's 6/10. And for convenience, for since it's just one decimal, so let me just use 0.6. Now I'll plug in x, dx dt, and sine theta in here to get d theta dt. Okay? And simplify. -0.5. And since this is trigonometry, the unit for angle is always radian or radians. So you put radian per unit of time, which is in seconds here, by the way. So radian per second. If asked, then you have to convert it to degrees, but we will only require you to use radians. But anyway, in degrees, you multiply it by 180/pi. You get approximately -28.65 degrees every second, meaning the angle is what? Decreasing because of the negative sign. Obviously, if the bottom is moving away from the wall, then the angle is also getting smaller and smaller. So -0.5 radians per second. Radian. Okay. So let's have another example, unless there's still a question on the current problem. So let's read the next one. An airplane is flying west at 500 feet per second at an altitude of 4,000 feet. A searchlight on the ground lies on the ground directly under the path of the plane. We will show the figure later. If the light is to be kept directed on the plane, how fast is the searchlight revolving when the distance of the plane from the searchlight is 2,000 feet due east? Let me show the free body diagram. So here's the plane. It's an altitude of 4,000 feet, moves parallel to the ground. Okay, it's always at 4,000 feet altitude. And this is the searchlight on the ground, which is always kept directed towards the plane, no matter where it is. Now we are being asked for how fast that angle is changing when this distance between the plane and the searchlight, okay, is 2,000 feet due east. It's not talking about this hypotenuse, this distance, okay? Well, actually, this should be the distance between the plane and the searchlight. But if you look at the way the sentence is constructed, we have there 2,000 feet due east. Okay, let me read that again. How fast is the searchlight revolving when the distance of the plane from the searchlight, this is the searchlight, this is the plane, is 2,000 feet due east. So it's speaking of this horizontal distance x. Now, what are we to find? We are to find the rate of change of this angle. And as I have said, the first thing you need to do is find the relationship between the variables. And here we have in the figure only two variables, x and theta. And can you think of a trigonometric function that relates x and theta here with the given value of 4,000 feet here for this side of the right triangle? They are the sides of this right triangle. So you know you can use either cotangent or tangent, and we usually use the major and not the co-function. So let's just use tangent, although you can use cotangent. So what is tangent theta? It's opposite over adjacent. Okay, so it's x over 4,000. And with that, we can differentiate with respect to time. Again, if you have a related rate problem, you always differentiate with respect to time, both sides. So if I differentiate tangent theta, we know it's secant squared theta. Don't forget to apply the chain rule, derivative of the quantity inside, which is just theta with respect to t. Differentiate the right hand side. This is just a constant, 1 over 4,000. So differentiate x with respect to time. Now, since we are looking for d theta over dt and not dx over dt, it is d theta over dt that we're going to solve for, unless this is were given and this is the one to be found. So solving for d theta over dt, we get this. Just divide by secant squared theta. You have this expression. And that means we can solve for this rate of change if we know the values of dx dt and secant squared theta. Now, it is not hard to see from the problem that this is given. Is it? Yes, it's given. So its value is 500 feet per second. So the airplane is flying west, okay, westward at this rate, 500 feet per second. And if x is this horizontal distance, then we know that this x is decreasing. So we assign a value of dx over dt equals negative 500. Flying westward, so x is the distance from this point. Of course, if the plane is already here, x would be negative in value. Either way, x is decreasing. Okay. Well, anyway, you can just analyze the sign in the final. You just have to discern or find out if the quantity is decreasing or increasing. And you know, if the plane is flying towards westward, then this angle here will be decreasing in value. So you expect a negative value for the rate of change later on. But anyway, this should be the proper sign for dx dt. And what else do we need? We need secant squared. Remember in the formula here, we need secant squared, but we don't have secant squared directly. Now I'll show you two ways to get secant squared. One is the one taught in the material. Actually, this is an example in the module. And that is by first getting tangent theta, which is the obvious one to find or to get, given this diagram here. X is 2,000, so tangent theta is, again, opposite over adjacent. So we just divide 2,000 by 4,000. So easy, just 1/2. Now to get secant squared, one thing you can do is use this Pythagorean identity. Well, don't be bothered by that. You can just search the 3 Pythagorean identities and bear them in mind, or write them down on an index card. But I'll show you a way in which you don't need to memorize or use identities. You'll just use triangles to solve for secant after I've solved the problem. So using this one, if you know tangent, you can get secant. So we know tangent, so we plug in. We get 5 over 4 for secant squared theta, and no need to get the square root since we need secant squared. So here's again, okay, that's 0.8. Here's again the one we found. So to get this rate of change, we need dx dt, we need secant squared. We have dx dt, we have secant squared here. Actually, we don't need x directly. We only need x to get secant squared. So plugging in, okay, you should get the value negative 0.1 rad per second. Okay, so the only challenge here really is in finding secant squared. So we did it by using Pythagorean identity, but we can use it by direct drawing of, or directly getting it from the triangle here. There's a question. Sir, is 5 over? Yeah, you're right. Uh, very, siguro lumilipad na yung isip natin, ano. O nga, 4 over 5 yung 0.8, ano? So, tama. Just notice here that I wrote 0.8 when it should have been 1.25. Now, I apologize again for that carelessness, but just do the adjustments. At least the important thing here is you know how to get d theta over dt by substituting the proper values for these quantities. So this should be just 1.20. So you have to adjust this. So instead of that, what is it? What should it be? It still, let me check. Ito sa calculator ko dito, unless you have it. Okay, so it's it's still correct. Oh, just so happened that it's still correct. Maybe I looked at the answer in the module, so I gave the same answer as the module, but okay. So here, I just use 0.8, but it should be 1.25 and you should get negative 0.1 still. Another way to get secant squared theta is by drawing this figure here. We already know that this is 2000, this is 4000. So applying Pythagorean theorem will give you this side, the hypotenuse, which is 2000 square root of 5. And we know that secant theta is hypotenuse over adjacent. You can just note that or just search it in Google or your textbook. So hypotenuse over adjacent. So this one here. And simplify. Okay. Now we need secant squared. So notice if you square secant, you get the same thing, 5 over 4. So if you don't want to make use of identities, then you can just use triangles to solve for the other trigonometric values of theta. Any more question? Another one? Okay, next. This is a very simple example, but I added this so that you can know how to differentiate implicitly with respect to time if you have two or more variables present in the equation on one side of the equation. Three variables here. We know that area is base times height. Anyway, first let's read the problem. So here's our rectangle problem. How fast is the area of a rectangle changing? So that's a direct question. If the base is increasing at the rate of 20 centimeters per second, so that's positive, while the height is decreasing, so you have to assign a negative, at the rate of 30 centimeters per second at this given instant. The instant when the base is 50 centimeters, height is 100 centimeters. Now, it doesn't mean that if one dimension is decreasing, that the area is decreasing. It actually depends. So there's a follow-up question there. Is the area increasing or decreasing? That's answer. Now, we know the area of a rectangle is base times height. So that's easy. All you have to do is differentiate again. Once you have the relation, remember, you differentiate next with respect to time. This is just a product, so we apply the product rule. first times derivative of the second plus the second times the derivative of the first. So it's base times derivative of the height plus the height times the derivative of the base, all with respect to time t. And well, good for us, all of those are given in the problem directly. Let's just write those. Base is 50, height is 100. Base is, where's that? Increasing at 20 centimeters per second positive, while the height is decreasing at rate of 30. So negative 30 there. If you put a positive here, your final answer will be wrong. So this time you have to be careful with the sign. So plugging into this formula for the rate of change of area, we get this and solve, we get 500 square centimeters per second positive. This is negative 1,500, but this is bigger, so 2,000 still makes it positive. So this is the answer to the first question. That's the rate. And notice the unit is square centimeters because it's area. And the answer to the second question, is it increasing or decreasing? Since it's positive in result, the area is increasing still. That means that. Any question? Okay, I only plan to discuss until differentials today to finish module 3. And then I believe today or tomorrow, we will be uploading the next module. By the way, for your next quiz, you have to study both modules 3 and 4. Okay? But for today, we'll only discuss until differentials, just to finish module 3. So, wait a minute. Fine. Okay, now differentials. Let's start by defining differentials. And it's just really another way of writing the derivative. Let's read. If y equals f of x is a function that's differentiable, then the differential of y, which we denote by dy, not delta y, it's differential of y. Or sometimes we just denote by df, since y equals f of x, is defined by the following equation here. dy, differential dy, is equal to f prime of x times dx, where we call the dx there as the differential of x. And it's simply the same as the change in x, or delta x. Now, this is a definition. Dx is just defined to be the same as delta x, whereas dy is not the same as delta y, but defined to be given by this equation. We will see that with some illustrations. But if you're gonna ask, where did this come from? Well, I won't give a technical, formal explanation, but if you divide by dx, what happens? You just get dy over dx equals f prime of x, which is just the same thing, right? Dy over dx is just the derivative of y with respect to x, and that's just f prime of x, written another way. So if you sort of like treat dy over dx as though it were a ratio, then you cross multiply dy dx to get this one. But anyway, the more important thing now for you to know is that this is the way dy, differential dy, is defined. It's the derivative times the differential dx. Now, what does this mean? And what application has differentials in real problems? Let's start by first giving a direct, or yes, a direct example where we are given a function and we're going to approximate the change in that function using differential. So this is the function f of x equals x cubed plus x squared minus 2x plus 1. Now, the thing to do is to approximate the change that will happen to y if our x value will change from the value 2.0 to the value 2.05. And note that we have here the word approximate the change. So to compare, we will also give the actual or the exact change in y. How do we get the exact change in y? Well, you compute directly the values of y. Okay. Now, the actual change in y is the delta y, the change in y. It's not the same as dy. But as we shall see, dy will approximate delta y very closely. Let's see. What's the change in y? Well, there are two values of x. X changes from 2 to 2.05. So this is just high school algebra, right? Where the change in y is y2 minus y1. So that's f of x2 minus f of x1. So this is the value at 2.05. This is the value at 2. If you subtract, you get the actual change in y. And if we do that, you have the following. So how do you get f of 2.05? Of course, you plug it in here, 2.05 cubed plus 2.05 squared, so on. You get this value, plug into 2 cubed, 2 squared, so on, you get 9. And you subtract. That's the increment, the change in y. Positive 0.717625. Now, notice to get the actual change, it takes a lot. You have to plug in, and the expression is not a very short or simple one. So sometimes it's better if we just approximate it when approximating is a lot easier or simpler. Now, to approximate delta y, we will use the differential defined a while ago by this equation. dy equals f prime of x dx. And as we have mentioned, dx is just the same as delta x. What is delta x? We know it's the change in x. X changes from 2.0 to 2.05. So if I ask you, what's the change in x? That's very easy. Change in x is 2.05 to minus 2, it's 0.05. And that coincides with dx. Again, in the definition, dx and delta x are the same. Now, this is x equals 2. Why did we choose 2? Because this is the starting value. And we want to know what will happen if we increase the value to 2.05 so that we assign a differential of x, a value of dx 0.05. Now, to get dy, we need f prime of x. So we differentiate f of x, applying the power rule. We have this. And so this is how it will go. Okay. Again, dy equals f prime of x dx by definition. So starting with the initial value of 2, so that becomes f prime of 2, and then the change in x, which is 0.05, gotten here ready, written here. So it's f prime of 2 times the change in x, 0.05. And f prime of 2 can be obtained by plugging into 2 into the derivative f prime of x found here. So, syempre, di-differentiate mo muna f of x para makuha yung f prime of 2. Kapag nakuha na si f prime of 2, then you multiply to the change in x, 0.05. That's 14 times 0.05, that's 0.7. Now, what does this do? It approximates the actual change. Note that the actual change is 0.717625. The approximate change is 0.7 and not bad. In fact, it's a good approximation since the change in x is very small. It's just 0.05. In fact, the smaller the change in x is, the better the approximation will be. Okay? So your question is, why not just use the actual values? Why bother with approximation? Well, there are problems where it's not that easy. Okay? As we shall see in the next example. So let's start with, okay, measurement. In science, you know that measurement can have an error. And what scientists do is simply measure physical quantities and then assign an error. So they say like the radius of the Earth is this long, plus minus certain kilometers. So how do they approximate the error? Well, they make use of the tools of calculus. So let's see that with this one. Let's read the example. The radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement. And somehow they, okay, uh, learned that or derived that the error is at most 0.05 cm. Good. Okay, very small room for error. But what's the error in the volume if we're going to also measure the volume by using the formula for volume and not actually measuring the volume itself by, let's say, immersing the sphere or putting water into the sphere and then measuring that amount. So let's see how we will use math to determine the approximation or the error in the approximation or the measurement, sorry, of the volume. Now we know the volume to be 4/3 pi r cubed. So suppose I don't want to measure volume directly and I'm just going to measure the radius. I know that there will be some error in the measurement of the radius, and thus there will be an effect. There will also be an error in the measurement of the volume. Now, using calculus, you can find the error in the measurement of the volume if you know the error in the measurement of the radius. The radius was measured to be 21 with this error. So to compute the error in the volume's measurement, we use the differential dV. How do you get the differential again? You differentiate the relation with respect to r, since r is the independent variable here, and we bring down 3, that becomes 4 pi, subtract 1, that becomes 2 times the differential r. That's definition. Now, this tells us that we can compute the error in the volume, or rather approximate the error, if we know the radius, measurement of the radius, and the error in the measurement. And we already know those. We are given 21 for r with this error. So dr is set to equal to delta r, changing r, 0.05. Plugging in here, okay? Just plugging in, then calculator work, you get that error. So if I'm going to measure or compute the volume, I expect at most an error of this much, 277 cubic centimeters. And since it's centimeters, then it's rather a very small error. If you compute, convert it to cubic meters, that would be like meters, centimeters. So move the decimal place 6 units to the left. Anyway, that's how you use differentials to approximate error. And last example for today, suppose you don't have a calculator, how do you approximate 101 if you only know the square root of 100? Now we can do that since 100 and 101 are very close to each other. And relatively, that change is small, right? It's in the 100, so a change of 1 is very small. So let's see. Well, this is a square root, so we consider the square root function. We assign that to be f of x, which is also our y, and use differentials. To get the differential dy, you differentiate square root of x, you know that to be 1/2 square root of x, of course, times the differential dx, where dx again is the change in x. So what's the differential one? Now, what's square root of 101? We will approximate it. Now, it's almost close, very close actually, to square root of 100. And we know that square root of 100 is 10. Now, if we're going to use square root of 100 to approximate square root of 101, we want to know the error. And we can approximate the error using differentials. So we will take x equals 100 to be our initial value. so that we can compute the approximate change in y when x changes to 101. So we will set dx, which is change in x, equal to 1, and compute dy. dy is 1 over 2 squared of x dx, plugging in 1 over 2 squared of 100 times 1, simplifying without a calculator, that can be done, 0.05, since this is just 10. So see, no calculator needed at all. So this tells us that the approximate change is 0.05. So that if I use 10 to approximate the square root here, I would have to adjust about 0.05 to get the square root of 101. So we say that the square root of 101 is approximately 10 plus that error, that approximate change. So it's about 10.05. And if you can verify with the calculator, correct to 4 decimal places or rounded off, 10.0499, which is very close. Okay, so that's it for today. You can just try the exercises at the end of the book so you can get more familiar with the practical applications of differentials to actual problems and numerical analysis. Actually, problems like this involve a branch of mathematics which we call numerical analysis. So does anybody have a question? If there's none, that's it for this session.
Thank you, sir.